Hello! So we're going to continue with the different types of comparison tests. Now we're going to talk about the limit comparison test. So previously we talked about just the regular comparison test. Now it is the limit comparison test. So I'm going to go to writing mode. So the comparison test worked by comparing the terms of the sequences that formed your series to figure out if the series will converge or diverge together. The limit comparison test works in a very similar way. So let's suppose that you have two different sequences, AN and BN. So suppose you have two different sequences, AN and BN. Okay? And what we're going to do is, so instead of with the comparison test, we looked at their reciprocals based. We started off with the two terms of the sequences, compared them, and then we took the reciprocal usually, which then you flipped the direction of the sign, and we were able to figure out which one was bigger or smaller. Now instead we're going to look at the ratio of the terms. So let's say you have AN and you have BN. That's going to be equal to some ratio, let's call it L. Now there are basically three different possibilities here with this ratio. It could be that AN over BN is equal to 1. It could be that AN over BN is less than 1. And it could be that AN over BN is greater than 1. So if AN over BN equals 1, that tells you that the terms of the sequence are exactly the same. If AN over BN is less than 1, that tells you that the ANs are less than BN. And if AN over BN is greater than 1, that tells you that AN is greater than BN. Okay? So you can start seeing that looking at the ratio of the terms of the sequence is very much like comparing the size of the sequence, just like what we did in the comparison test. So the idea here is we start asking ourselves like, so what if we took the limit of this? Because this is just looking at particular terms. What if there's something that happens as you look at the limit? So this is what the limit comparison test says. Let's suppose that the limit as n goes to infinity of AN over BN. Let's say that it equals infinity. That the limit does not exist, or it tends towards infinity. Well, what does that mean? It means that, actually, I'm sorry, we should back up. Let's not do that one first. Let's say that the limit is equal to some number L that's not equal to 0. So what that means is that at some point the AN term is approximately equal to L times BN, which means that one in some sense is basically a constant multiple of the other. Now, because they're constant multiples of the other, we can imagine that if you're taking the series, then these are approximately equal to each other. Okay, so because they're equal to each other approximately, they're basically multiples of each other. That means if one converges, the other converges, and if one diverges, the other diverges. So in this case, either the series will converge or diverge together. And this should make sense because if their ratio is equal to a number not equal to 0, the AN will be equal to L times BN, which means that their sums will be equal to each other. And if the sums are equal, then they should either converge or diverge together. So let's call that case 1. What about case 2? So let's look at the limit of the ratio. Let's say that the limit is equal to 0. If the limit is equal to 0, That means the number on bottom is getting big compared to, the term on bottom is large compared to the term on top. The bn's are greater than the an's. So what does that mean? Well, we can use the comparison test. If the series of bn converges, then so does the series of an. And that's what we can say. So if the limit of the ratio is equal to 0, that means the terms on bottom are larger. If the larger term converges, then so does the smaller terms. Let's talk about the third case. Suppose the limit as n goes to infinity of an over bn is equal to infinity or does not exist. So what does that mean? It means the term on top tends towards a much larger value compared to the term on bottom. So you get that the an's are bigger than the bn's. So if the an's, so we can use the comparison test now. If the an's, if the series of bn diverges, then so does the series of an. Now why is this? Well, the bn's are smaller, and if a smaller thing adds up to infinity, then so must a larger thing. So notice this is always done for the second ones, it's done in terms of what you know about bn. Okay, so you need to know if bn converges or diverges, and that tells you something about an. For the first one, if it's not equal to 0, then whatever happens to one happens to the other. So let's do an example. So let's figure out the convergence or divergence of these sequences. So we'll look at the sum of n equals 1 to infinity of 1 over square root n plus 1. Okay. So what we need, so remember, the one that we want to determine we will call an. So now we need to figure out a bn to compare it to. And sometimes this is like sort of an art to figure it out. Usually when you do this, you want to get rid of any constant terms on the bottom, so let's compare it to 1 over square root n. Why do I want to compare it to square root 1 over square root n? Because that's a p-series, it's 1 over n to the half, and we know that this diverges. Okay, so this will be our bn. We know that bn diverges. Okay, and on top of that, we actually know that the square root of n is less than the square root of n plus 1, which means when we take the reciprocal, you can change the sign. So what do we now know? We know that the terms of bn are greater than the terms of an, and let's take the limit. So we're going to do the limit as n goes to infinity, and what we want is an, the limit of the ratio of an over bn. So the limit as n goes to infinity of 1 over square root n plus 1 divided by 1 over square root n. Let's do that calculation here on the side. So it'll be 1 over square root n plus 1 times the reciprocal root n over 1. So you get square root n over square root n plus 1. So we get the limit as n goes to infinity, square root n over square root n plus 1. Okay, using L'Hopital's rule, you find very quickly that this is equal to 1. Okay, and we were told that according to the limit comparison test, if the limit of the ratio equals 1, they either converge or diverge together. We know that Bn diverges, so must An. So the limit comparison test tells us that our series diverges. Why is that? Well, we compared it to a series which diverges, and the ratio of the limit is equal to 1 by the limit comparison test that tells us they either both converge or diverge together. The thing we're comparing it to diverges, so it must diverge. Let's do another example. Let's investigate the convergence or divergence of the series sigma n equals 1 to infinity of 2 to the n plus 1 over 3 to the n. Okay, so this will be our an. Okay, so we need some sort of bn, which we know will converge or diverge. So looking at this, it looks almost like the geometric sequence, which is 2/3 to the n, which we know converges. So we'll set this as our bn and take the limit of the ratio and see what happens. So we'll do the limit as n goes to infinity of an over bn, which is the limit as n goes to infinity of 2 to the n plus 1 over 3 to the n, all divided by, let's write this as 2 to the n over 3 to the n. Okay, we can compute this off on the side. This is going to be 2 to the n plus 1 over 3 to the n times the reciprocal, which is 3 to the n over 2 to the n. Well, those 3 to the n's cancel, leaving us with 2 to the n plus 1 over 2 to the n, which will give us 2 to the n over 2 to the n, which is 1, plus 1 over 2 to the n. So now we can take our limit. This will be equal to the limit as n goes to infinity of 1 plus 1 over 2 to the n. The limit of 1 is just 1. The limit of 1 over 2 to the n as n goes to the infinity will be 0. So you get 1, which means our original series converges. Why? Because our other series converges and the ratio of the limits was 1. Let's do another example. Let's look at the convergence or divergence of the series sigma n equals 1 to infinity of natural log of n over n squared. Okay. So sometimes it's hard to, so this will be our an. Sometimes it's hard to come up with the bn, but looking at this, we know maybe we can compare it to 1 over, we have several options. We can compare it to 1 over n squared. So if that's our bn, we need to look at an over bn, which would be natural log n over n squared divided by 1 over n squared, which would give us natural log n over n squared times the reciprocal of 1 over n squared, which would be n squared over 1. The n squareds would cancel, leaving us with natural log of n. Okay, that limit would go to infinity. So if the limit goes to infinity, then we can only make a statement if the bn diverges. Well, the bn doesn't diverge, so that's not going to work. So Why don't we try a different Bn? We'll try our Bn now just to be 1 over n. Because we know that that actually diverges. So we can look at an over bn. That will give us natural log n over n squared divided by 1 over n, which will give us natural log n over n squared times the reciprocal of 1 over n, which is n over 1. That will give us the natural log of n over n. Okay. So let's take the limit of that. The limit as n goes to infinity of an over bn equals the limit as n goes to infinity of natural log n over n. Using L'Hopital's rule, you can see that what you'll get is 0. This actually makes sense if you look at the graph. We know that the graph of natural logarithm is always less than the graph of n. Now, if the limit equals 0, we know that if bn let me scrap that example, sorry.